Buried deep within the earth, hidden in volcanic chambers, meteorite fragments, and the crushing darkness of the mantle, lie minerals so rare, so extraordinary, that most people will never hear their names. These are not the familiar gems found in jewelry stores. They are crystals born in the planet's most violent moments, shaped by pressures that can crush steel and temperatures hotter than molten lava. Some bend light like living prisms. Some hold secrets older than the Earth itself. Others formed in the hearts of exploding stars long before our planet even existed. In this video, we journey far beyond the world of ordinary geology. We'll uncover minerals that shouldn't exist, minerals that challenge the limits of physics, chemistry, and imagination. From gemstones rarer than any diamond, to crystals forged in meteor impacts, to minerals with magnetic, radioactive, or even electric personalities, these are the natural wonders that redefine what a mineral can be. Prepare to step into a hidden universe beneath your feet, one filled with impossible structures, cosmic origins, and properties that defy everything you thought you knew about Earth's materials. Welcome to the most extreme minerals you never knew existed. Let's begin the descent into the extraordinary. Nature's limits, minerals formed under the most extreme conditions. Deep beneath the Earth's surface lies a hidden world where unimaginable heat and pressure reshape matter into forms that could never exist at the surface. Minerals born in these environments carry the signatures of the extreme forces that created them, and each one reveals a different chapter of the planet's inner history. This section explores how these minerals form, the geological environments that produce them, and why their structures are unlike anything created under ordinary conditions. Far below the crust, in the transition zone of the mantle, between roughly 410 and 660 kilometers in depth, pressures rise to hundreds of thousands of atmospheres. At these depths, ordinary minerals become unstable, forcing atoms to rearrange into denser configurations. Ringwoodite is one of the most remarkable products of this environment. Its compact atomic structure can trap water within crystal defects, and small inclusions found in diamonds suggest that enormous reservoirs of water may exist deep inside the Earth. This discovery has transformed our view of the planet's internal water cycle. Another mineral shaped by extreme pressure is stishovite, a high-density form of quartz. Unlike the transparent, hexagonal quartz familiar at the surface, stishovite forms only when silica is compressed with extraordinary force, most commonly during meteorite impacts. Its presence in crater sites provides evidence of ancient cosmic collisions and allows geologists to reconstruct the violence of events that altered entire landscapes in milliseconds. At even greater depths, the mantle gives rise to another enigmatic mineral, majorite. Formed under both extreme pressure and high temperatures, majorite reveals the circulation of material between the deep mantle and the upper layers. When volcanic eruptions bring fragments of this mineral to the surface through mantle xenoliths, they offer a direct look into regions otherwise inaccessible to science. Volcanic environments themselves also push minerals to their limits. Near the roots of massive volcanic systems, temperatures can exceed 1000 degrees Celsius, enabling the crystallization of minerals like cubic zirconia and natural moissanite, which require conditions too unstable to persist in the outer crust. These minerals tell a story of rapid heating, melting, and cooling under the influence of immense thermal energy. Even diamonds, the most iconic of all gemstones, are products of extremes. Natural diamonds form more than 150 kilometers deep, where carbon atoms are subjected to pressures so high that they lock into the tightly bonded lattice that gives diamonds their unsurpassed hardness. Without the explosive upward force of kimberlite eruptions, these crystals would remain forever sealed in the mantle. Together, these minerals form a category defined not by rarity alone, but by the impossible environments required for their creation. Each specimen that reaches the surface acts as a geological messenger, carrying information from regions far beyond human reach. Through them, scientists uncover the hidden mechanics of a dynamic and restless planet, one whose most extraordinary processes often happen far out of sight, in the deepest and most extreme corners of the Earth. The rarest and most exotic mineral structures on Earth. While countless minerals are abundant and well known, a select group exists at the very edge of rarity, minerals so scarce, unusual, or structurally complex that many people will never encounter them outside of scientific literature. These minerals are not simply hard to find. They often form only in tiny geological windows where specific elements, pressures, and temperatures align for a brief moment in Earth's history. Their beauty, atomic architecture, and extraordinary chemical compositions make them some of the most exotic substances the planet has ever produced. One of the most famous examples is pinnite, once considered the rarest mineral on Earth. When it was first described in the 1950s, only a single specimen was known. Pinnite's structure includes an unusual combination of zirconium, boron, and rare trace elements such as vanadium and chromium. This unusual chemistry makes its formation incredibly difficult. The ingredients must meet in exactly the right proportions. Even today, despite new discoveries in Myanmar, gem-quality crystals remain almost unbelievably scarce. Pinnite embodies the idea of geological coincidence, a mineral born out of nearly impossible circumstances. Another extraordinary mineral is tophyte, which became famous for being discovered not in the field, but in a gem collector's workshop. Its optical properties were so unusual that it initially appeared to be a misidentified spinel. Only later did researchers determine that it was a completely new mineral species. Tophyte's hexagonal crystal structure contains both beryllium and magnesium, an uncommon pairing that requires a highly specific chemical environment to crystallize. As a result, natural tophyte gemstones are estimated to be 1,000,000 times rarer than diamonds. Even more exotic are minerals that owe their rarity to conditions found only in meteorites. Hibonite, for example, is one of the oldest minerals formed in our solar system. Found inside primitive meteorites, it crystallized within the first 1,000,000 years after the Sun's birth. Its crystal structure contains refractory elements like titanium, calcium, and aluminum, which condense only in extremely high-temperature nebular environments. Holding a piece of hibonite is holding a fragment of preplanetary history. But Earth itself has produced minerals that are equally mysterious. Geomegevite, with its pale blue to colorless hexagonal prisms, forms in rare pegmatite zones where the chemistry fluctuates rapidly during crystal growth. Because the mineral requires both boron and aluminum while simultaneously avoiding contamination from more common competing elements, geomegevite crystallizes only in isolated pockets of the Earth's crust. Each crystal is a geological accident preserved in pure, elegant form. There are also minerals whose rarity arises from structural complexity. Eudialyte, for example, is part of a group of minerals with extraordinarily intricate atomic frameworks involving rings, chains, and clusters of silicate units. These structures can incorporate dozens of chemical elements at once, making every crystal a tiny, natural laboratory of chemical substitution. Their vibrant colors, reds, purples, and magentas, reflect this complex chemistry. Some exotic minerals challenge even our fundamental understanding of how crystals grow. Parasite and zechserite represent minerals with odd symmetry, unusual layer arrangements, or rare element combinations that push the boundaries of mineral classification. Their existence tells us that Earth's chemical environment is far more flexible and diverse than once believed. Collectively, these rare and exotic minerals reveal the extraordinary range of chemical possibility present on our planet and beyond. They form only when nature's variables align perfectly, momentary intersections of temperature, pressure, elemental abundance, and time. Each crystal is not just a mineral specimen but a record of a fleeting event, preserved for millions or even billions of years. Through their study, mineralogists gain insight into the evolution of Earth, the solar system, and the endlessly innovative forces that shape the natural world. Mind-bending properties, minerals that defy expectations. Not all minerals owe their fame to rarity or extreme origins. Some astonish scientists and collectors alike because their physical or chemical properties seem almost impossible. These are minerals that behave in ways we don't expect from ordinary solids, minerals that bend light, generate electricity, glow in the dark, attract metal, resist radiation, or exhibit strengths beyond anything engineered by humans. Their unusual behaviors challenge our understanding of matter and reveal the incredible versatility of nature's chemistry. One of the most striking examples is lodestone, a naturally magnetized variety of magnetite. Long before humans understood magnetism, ancient civilizations discovered that certain stones could attract iron and align themselves with Earth's magnetic field. Lodestone is the earliest known form of a compass, and it forms only when magnetite is struck by lightning or exposed to powerful magnetic fields during crystallization. Its ferromagnetic properties emerge from the unique arrangement of iron ions in its crystal lattice, an arrangement that remains stable over geological timescales. Another mineral that defies expectations is uraninite, a primary ore of uranium. At first glance, it appears as nothing more than a black, opaque crystal. But internally, uraninite undergoes constant radioactive decay, releasing heat and altering its own structure over millions of years. Some uraninite specimens even contain tiny inclusions of helium, produced as a byproduct of alpha decay, and these inclusions help scientists determine the age of the Earth. Through radiometric dating of uraninite and related minerals, geologists uncovered one of the most important scientific truths, that the Earth is more than 4.5 billion years old. Equally fascinating are minerals that interact with light in surprising ways. Fluorite, for example, can fluoresce in brilliant blues, greens, and purples when exposed to ultraviolet radiation. The phenomenon results from trace impurities and defects in the crystal lattice that temporarily trap electrons. When these electrons return to their normal state, they release energy as visible light. This simple atomic mechanism produces one of the most visually stunning mineral effects known. The name fluorescence itself was inspired by fluorite's behavior. In contrast, bismuthinite and certain sulfide minerals display unusual electrical properties. Some act like natural semiconductors, allowing small electrical currents to pass through them. These minerals possess a delicate balance between metallic bonding and covalent structures, placing them on the boundary between conductor and insulator. Their study contributed to the early understanding of solid-state physics, paving the way for modern electronics. There are also minerals whose hardness or resilience borders on the impossible. Moissanite, originally discovered in a meteor crater, is nearly as hard as diamond. Its extreme durability comes from the strong covalent bonds in its silicon carbide structure, bonds arranged in a pattern that resists deformation even under immense pressure. Its discovery in extraterrestrial material suggested that silicon carbide crystals could form in the atmospheres of dying stars, expanding our understanding of cosmic mineralogy. Another example is tourmaline, famous for its pyroelectric and piezoelectric properties. When heated or mechanically stressed, tourmaline generates an electrical charge at its crystal ends. This phenomenon, caused by asymmetry in its atomic structure, was once used to detect infrared radiation and is still applied in sensitive electronic components. Tourmaline demonstrates that minerals are not static objects but dynamic systems capable of responding to physical forces. Even optical illusions arise from natural crystals. Ulexite, known as the TV rock, can transmit images from one surface to another through parallel fiber-like crystals, functioning like a natural fiber optic cable. When placed over a printed surface, ulexite projects the image to the top, creating the impression that the text appears inside the stone. This remarkable effect results from internal pathways that guide light with almost no scattering, an ability once thought unique to manufactured fiber optics. Collectively, these minerals show that nature is not bound by our expectations. They twist magnetic fields, manipulate light, generate electricity, and preserve atomic secrets billions of years old. Their unusual properties push the boundaries of physics, chemistry, and geology, reminding us that even the simplest-looking rock may contain phenomena capable of reshaping our understanding of the natural world.